in this problem we have a system. Its eigenstates are specified by two non-negative integers n1 and n2. Energy of system is given. En is equal to n1 plus 1 by 2 h cross omega plus n2 plus 1 by 2 2 h cross omega. We have to find the probability of energy of the system being less than 4 h cross omega at temperature T. To solve this question, first of all we have to enumerate or list all the states with energy less than 4 h cross omega. We are told that n1 and n2 are non-negative integers, which means n1 and n2 can have values 0, 1, 2, 3, etc. When n1 is equal to 0 and n2 is equal to 0, E00 equal to 1 by 2 h cross omega plus 1 by 2 into 2 h cross omega is h cross omega. This is equal to 3 by 2 h cross omega. When n1 is equal to 1 and n2 is equal to 0, we have energy is equal to 1 plus 1 by 2 h cross omega is 3 by 2 h cross omega plus n2 is 0, 0 plus 1 by 2 into 2 h cross omega, that is h cross omega. This is equal to 2.5 h cross omega, or you can write 5 by 2 h cross omega. When n1 is equal to 0 and n2 is equal to 1, we have 1 by 2 h cross omega plus n2 is 1, 1 plus 1 by 2 is 3 by 2, 3 by 2 times 2 h cross omega. This is 3 h cross omega. Therefore this is equal to 3.5 h cross omega, or you can write 7 by 2 h cross omega. When n1 is equal to 2 and n2 is equal to 0, energy is 2 plus 1 by 2 is 5 by 2, 5 by 2 h cross omega plus h cross omega. This is equal to 3.5 h cross omega. For all the other states other than these 4 states, we have energy is greater than 4 h cross omega. You can check this. When we take E11, which is when n1 is equal to 1 and n2 is equal to 1, we will get 3 by 2 h cross omega plus 3 h cross omega, which is greater than 4 h cross omega. Similarly, if you take 2, 1, 1, 2 or any other state, you will get energy is greater than 4 h cross omega. So these are the valid states. These are the 4 valid states for which energy is less than 4 h cross omega. So the step 1 was to enumerate or list all states with energy less than 4 h cross omega. We have done that. Now the next step is to calculate probabilities for each state En. So probability of occupying nth state at temperature T, this is equal to e raised to minus beta En divided by Z. Here Z is the partition function and beta is equal to 1 by kT. In this case, probability of occupying state specified with integers n1 and n2, this is equal to e raised to minus beta E n1 n2 divided by Z. P00, when n1 equal to 0 and n2 is equal to 0, we have e raised to minus beta. E00 is 3 by 2 h cross omega, 3 by 2 h cross omega divided by Z. This is equal to, in the question it is said that alpha is equal to exponential of minus h cut omega upon kT and beta is 1 by kT, so this is e raised to minus 3 by 2 h cross omega upon kT divided by Z. which is equal to e raised to minus h cross omega upon kt is alpha. Therefore, this is alpha raised to 3 by 2 divided by z. Now let us calculate the probability of occupying state specified by the integers 1 and 0, p10. This is equal to e raised to minus beta e10. E10 is 2.5 h cross omega, which is 5 by 2 h cross omega. 5 divided by 2 h cross omega divided by z. This is equal to e raised to, this is equal to alpha raised to 5 by 2 divided by z. Similarly, we can calculate P01. P01 is equal to e raised to minus beta E01. E01 is equal to 3.5 h cross omega, which is 7 by 2 h cross omega. 7 by 2 h cross omega. This is divided by z. This is equal to alpha raised to 7 by 2 by z. Probability of 20 is equal to e raised to minus beta E20. E20 is also 7 by 2 h cross omega. Divided by z. This is equal to alpha raised to 7 by 2 divided by z. Now we have to calculate the probability that at temperature T the energy of system will be less than 4 h cross omega. Let's specify this probability by, let's denote it by P of E less than 4 h cross omega. Then this will be equal to P00 plus P10 plus P01 plus P20. This is equal to P00 is alpha raised to 3 by 2 by z, P10 is alpha raised to 5 by 2 by z, P01 is alpha raised to 7 by 2 by z, P20 is alpha raised to 7 by 2 by z. Therefore, we have the sum equal to alpha raised to 3 by 2 plus alpha raised to 5 by 2 plus 2 times alpha raised to 7 by 2 the whole divided by z. Now you have to find what the partition function z is, and then you have to substitute it here, then you will get the probability. Z is defined as z is equal to summation over r e raised to minus beta er, where er is the energy of rth state. In our case, the system state is specified by two integers, and each integer can have any non-negative integer values from 0 to infinity. Therefore, there will be two summations. Z will be equal to summation over n1 equal to 0 to infinity, summation over n2 equal to 0 to infinity, e raised to minus beta en1 n2. En1 n2 is n1 plus 1 by 2 h cross omega plus n2 plus 1 by 2 2h cross omega. Let us write beta as 1 by kt, the whole divided by kt. This is the partition function. Now we can write exponential of a plus b is equal to exponential a times exponential b. Therefore, if we use this here, we can write z is equal to summation over n1 equal to 0 to infinity e raised to minus n1 plus 1 by 2 h cross omega upon kt times summation over n2 equal to 0 to infinity e raised to minus n2 plus 1 by 2 n2 plus 1 by 2 2 h cross omega divided by kt. This is equal to, we can take the term which is not depending on n1 outside, e raised to minus 1 by 2 h cross omega upon kt times summation n1 equal to 0 to infinity e raised to minus n1 h cross omega upon kt times e raised to minus h cross omega upon kt. This is not depending on n2, so we took it outside. Summation n2 equal to 0 to infinity e raised to minus n2 2n2 h cross omega upon kt. Let us make some space here. This is our partition function. Here the first term e raised to minus 1 by 2 h cross omega upon kt, this is alpha raised to 1 by 2. So z equal to alpha raised to 1 by 2 times, this is e raised to minus h cut omega upon kt, this is alpha, and this is a sum of geometric series, infinite geometric series. And in the case of a geometric series, sum is given by s is equal to a divided by 1 minus r, where a is the first term and r is the common ratio. Here the first term is e raised to minus 0, which is 1, divided by 1 minus r is common ratio is e raised to minus h cut omega upon kt, which is alpha, times e raised to minus h cut omega upon kt is alpha, times again we have another geometric series summation, infinite geometric series summation. Here first term is again 1, because when you put n2 equal to 0 you will get e raised to minus 0, which is 1, divided by 1 minus r, common ratio here is e raised to minus 2 h cross omega upon kt, which is alpha square. So this is the partition function that we are getting. This is equal to alpha raised to 1 by 2 times alpha is alpha raised to 3 by 2, divided by 1 minus alpha times 1 minus alpha square. Let us write it in the next slide. Z is equal to alpha raised to 3 by 2 divided by 1 minus alpha times 1 minus alpha square. Let us put the value of z in the expression for probability. We will substitute z here. Then p will become in the numerator we have alpha raised to 3 by 2 plus alpha raised to 5 by 2 plus 2 times alpha raised to 7 by 2 divided by, in the new denominator we have z, which is alpha raised to 3 by 2 divided by 1 minus alpha times 1 minus alpha square. This is equal to When you divide alpha raised to 3 by 2 by alpha raised to 3 by 2, you will get 1. When you divide alpha raised to 5 by 2 by alpha raised to 3 by 2, you will get alpha. And when you divide alpha raised to 7 by 2 by alpha raised to 3 by 2, you will get alpha square. There is a 2 also. And this term, it will come to the numerator. So this is equal to, Z is equal to 1 plus alpha plus 2 alpha square times 1 minus alpha times 1 minus alpha square. Actually, I made a mistake here. This is not Z, this is P. This is P of probability that we needed to calculate. This is coming out to be 1 plus alpha plus 2 alpha square times 1 minus alpha times 1 minus alpha square. Now let's compare with the options given. In the option 3, we have 1 minus alpha square. We have also 1 plus alpha plus 2 alpha square. But here we have 1 minus alpha, but in the option it is 1 plus alpha. In the option 4, we have 1 plus alpha plus 2 alpha square, 1 minus alpha square, but it is whole square. What we can do is we can substitute 1 minus alpha square is equal to 1 plus alpha times 1 minus alpha. This implies P will become 1 plus alpha plus 2 alpha square times 1 minus alpha. Instead of 1 minus alpha square, put 1 minus alpha into 1 plus alpha. This will give you P is equal to 1 plus alpha plus 2 alpha square times 1 minus alpha the whole square times 1 plus alpha. Therefore, the correct option here is 1 minus alpha the whole square times 1 plus alpha times 1 plus alpha plus 2 alpha square. Yes, this is correct. Option 4 is the correct answer here.